Oops. So instead of continuing the last video, I accidentally hit the stop button. So this is a continuation of the last video. We were just finishing up the 3.2 summary, and I just wanted to do a couple of exercises, but then the video stopped before we actually did any. So let's take a look at some of the book problems here. Is that focused? Okay, so we know how to compute the Wronskian between two functions, right? So that should be straightforward. Determine the longest interval in which the given initial value problem is certain to have a unique twice differentiable solution. Do not attempt to find the solution. So you remember how to do those? This is existence and uniqueness. And so we just need to be sure that our functions are continuous on the interval that's containing the t naught. Okay, so for example, this first one, once you divide by t, right, you have to make sure that t equals 0 is not included. So if the initial value is 1, that means your interval is going to be the interval from 0 to infinity, not including 0. Good. That's similar to all these. This number 13 is just taking two solutions, and you're going to show that these are two solutions to this differential equation. By the way, that is a linear homogeneous differential equation, right? And then you're going to show that the sum is also a solution for any C1 and C2. So this is kind of a manual thing. So take this to be your general function, plug it into your differential equation, and see that everything works out. Of course, you know it is, right? Because it's a linear operator. Okay, that's just practice, though. Let's see, 1 and t to the 1/2 power are two solutions to this differential equation. Show that C1 times the first function plus C2 times the second is not in general solution of this equation. What? What? Doesn't that contradict theorem 3.2.2? No. And the reason is, can you see why? What kind of a differential equation is this? Is this linear? Absolutely not. Okay. I'm probably getting carried away. It's getting late. This one's kind of an interesting problem. I usually assign it and people get confused about what's going on here. Can y equals sine of t squared be a solution on an interval containing t equals 0 of this equation with continuous coefficients? Explain your answer. Now, the way to look at this is if y is equal to the sine of t squared, then you can actually just plug everything into this differential equation, and you can actually look to see what does p and q have to be in order for this to be a solution to the differential equation, and then you can answer the question that way. Did you catch that? So you would actually try to plug this solution into this differential equation and see what you get. Okay, let's see. If the Wronskian of f and g is 3e to the... I'm giving away all the homework problems. Okay, how about we should do one of these. How about number 17? So if the Wronskian of f and g is 3e to the 4t and f of t is e to the 2t, find g of t. Good. So let me rewrite that. Y1, or I'm saying that f equals e to the 2t, and the Wronskian is 3e to the 4t. Find g. Oops. Sorry about that. Do you remember how to do this? This is exactly the same problem as if I give you one solution to the differential equation and we want to find the second solution. But in this case, the book is already giving you what the Wronskian was. Do you remember what that problem was? This was problem number 17 if you want to look at it later. Okay, so the idea is that you can compute W using the definition, and then we can set the two different versions of Wronskian together. So the Wronskian of e to the 2t and g, by definition, is e to the 2t g, 2e to the 2t g prime. So we get e to the 2t g prime minus 2e to the 2t g, right? And so now these two things have to be equal to each other. So we get that e to the 2t g prime minus 2t 2e to the 2t times g equals 3e to the 4t. Good. And now get rid of the e to the 2t's. G prime minus 2g equals 3e to the 2t. Good. This is a linear differential equation. The integrating factor is e to the minus 2t. So g times e to the minus 2t prime is equal to 3 times, oh, it's just 3. That makes it easy to do. The integral is 3t plus c. And so g now is 3t e to the minus 2t plus 2t, plus c e to the 2t. Now, here's the question. Do I need to make g have this arbitrary piece in it? Or can I just can I choose c to be anything? And the answer is you can choose c to be anything because we're just looking for a particular version of g. And so notice that e to the 2t is already represented. Oops, sorry, it ran off the page there. E to the 2t is already represented as f of t. So we can just set c equal to 0 in this example. And so our g then is going to be 3t e to the 2t. And in fact, if f and g are solutions to a linear first order differential equation, you could also throw away the 3. But in this case, we don't know that. So we'll just keep the g there. Okay. And in fact, you could keep it generic since we don't know that we're taking all linear combinations too. So maybe either way. All right. Is there another homework problem that we might want to look at? Let's see. How about, 19 and 20 are kind of fun to try, but there's a lot of algebra involved there, so unless you got a lot of time. Here's a good one, 38 through 40. Let's see if I can get that in your view there. So suppose that y1 and y2 are two functions that are 0 at the same point in the interval. Then they cannot be a fundamental set of solutions on that interval. I wonder why that would be. Do you know why? It has to do with the Wronskian, right? Because we know that the Wronskian is the determinant of y1, t0, y2, t0, y1 prime of t. In fact, we could just put a t there. And then y2 prime of t. So what this is saying in number 38 is that what happens if these two numbers right here are 0? What's the Wronskian going to be? The Wronskian will be 0, right? If this is 0 and this is 0, then that's 0. And so do they form a fundamental set then? They do not. Similarly, prove that if y1 and y2 have maxima or minima at the same point in I, they cannot be fundamental set of solutions on that interval. Do you see why that would be? Because if they had the same maxima or minima, that would mean that the derivatives are 0 at the same spot in time, and then you would have two zeros in the bottom. And so the determinant again would be 0. Okay, so that's kind of a cute way of looking at 38 and 39 are kind of cute ways of looking at implications of the Wronskian being equal to 0. Do we have time for one more? How about 34? Oh, 35. We'll do an odd one. Let's see, y1 and y2 are a fundamental set of solutions to t squared y double prime minus 2y prime plus 3 plus t times y equals 0. And the Wronskian of y1 and y2 is equal to, at the point 2, is equal to 3. Find the Wronskian of y1 and y2 at the point 4. Well, given this differential equation, I know what the Wronskian is by using the Abel's theorem. So the Wronskian is going to be c times the integral of minus, that's 2 over t squared dt. Oops, that's not very good there. Hang on for 1 sec. Okay, so this is minus p of t. Oop, I see a sign wrong, right? I need a plus sign there. So what's that going to be? The integral of 2t to the minus 2 power will give us, I'm running, it's hard to write in this little space here. Let me get rid of this space. Okay, so that's going to be, sorry about that, minus 2t to the minus 1. Now I don't need a plus c here, right? Because I just need one antiderivative for my Wronskian. And so my Wronskian is going to be ce to the minus 2t to the minus 1. Okay, so that's the Wronskian at time t. And so what we're given is that the Wronskian at time, what time? At time 2 is 3. So why is that information given to us? Because using that information, I can figure out what the c is. So the Wronskian at time 2 is 3, and it's also equal to c e to the minus 2 over 2, right, which is e to the minus 1. Therefore, c is equal to 3e, right? Good. And so finally, what is the Wronskian at 4? The Wronskian at 4 will be 3e, that's my constant, times e to the minus t divided by 4, right? We shouldn't leave it like that. Is that 3e to the 1 times e to the minus 1/2 e to the 1/2 power? Good. There it is. We can have some fun with Abel's theorem. Okay, I better stop there. I probably got way too many videos for this section.